finish or to go back to some points we saw yesterday when I had no time since I lost my train. Well, we remember that in the last lesson, we worked with a new index for water structure, which basically consisted in an energy-based indicator, which was able to discriminate molecules into two classes. One of them were structure, which basically had a well-ordered tetrahedral structure, and the other ones were molecules with a defective environment. They were defects, and basically they had three hydrogen-bonded neighbors. They were lacking one hydrogen bond. But then we decided to go beyond the single molecule level to a multimolecular indicator, since which was shown here is behavior, but this was before this. This is not working. Let me see if it was, no. No, it does not work. It's plugged.
Try the laser.
Yeah, the laser works. It's not better. I'm not seeing it here. There? To the computer? It's strange. It's doing something here, but... oh, no. Now it's working. Okay, now it works. And so we decided to look at the environment of these different molecules, and we kept for the structure molecules, the ones which were surrounded by other structural molecules up to the second neighbor shell. And we decided to look at how different structural molecules went to the mean defect fraction. This is a defect correlation function, and you see that basically when you have a structured molecule which is surrounded by a defective one, or in its first shell or in its second shell, they quickly went to the mean defect fraction. This tells us that basically the system is behaving as these molecules here are conforming a frozen sea of structured molecules, which demand very long times and very long range events to relax, while the others basically interconvert between them, and because they are involved in short range local events. To see this, we had to define these time scales, which I did not, since I did not have time last lesson. And I'm sorry, I'm going to steal a bit of Paola's subject, but I'm going to skip a lot of things. But this is even worse, since I'm going to steal also one of her images here. So, well, I'm sure Paola is going to explain this in great detail, but basically what we have here is the mean square displacement function for the system, and we have three regimes, as was mentioned by Paola before. We have a ballistic regime when the molecules find that they are caged by their first neighbors. Then you have this occurs at very short times and very short length scales. Then you have a caging regime when you are in the supercooled regime, but if you are at high temperature, you change from this ballistic regime directly to a diffusive one. And in the supercooled regime, you change from a ballistic to a caging regime, and then finally to a diffusive regime. And this change is basically occurs at a time scale which is called T star, which is the time scale at this, when the system is most dynamically heterogeneous, which can be is defined, and you are going to see it later on, but basically what happens here is that the system has dynamics that vary dramatically from one region of the sample to another. This is perhaps what Paola has told you, was going to talk. When you look at the Van Hoff correlation function, when you have very short times, this is Gaussian, and this also happens at long times, but when you are intermediate times, you have a difference between the Van Hoff function and the Gaussian function. That is, the system is behaving in a non-homogeneous way, and this happens mostly when you have this time scale called T star, which can be calculated by a non-Gaussian parameter. So this time scale marks the time when the system is behaving most heterogeneously. That is, when you have regions that change a lot ones from the others. Sorry. And when you look at what happens at that time, this is here, you have that some 10% of the system is moving, from 5 to 10% of the molecules are moving, the rest are not mobile. And when you go to the diffusive regime, you can get the final structural relaxation of the system that occurs when all the molecules have changed, have moved one interparticle distance. And that's called the alpha relaxation time that I'm sure Paola is going to talk. Thus, when we are at T star, we have that only 5 to 10% of the molecules move. They are arranged in clusters, and it is this tells you that you are in a position where long-range events are beginning to set in. We were here, sorry. To set in. And so when you see that these guys here and here go to the mean defect fraction. They become defects very quickly, much before T star, and only these ones go to the mean defect fraction at time scales that are much larger. So you see the system is behaving in a sense that all these are basically frozen in the time scale we are studying, and these ones interconvert between them and the defect molecules. That is, they are taking part of short-range events, since they have a very close defect in their cage, in their neighborhood, and they change one from another. And that's why we decided to look only at these ones, and which correlate with the fraction of structural molecules as a function of temperature. Okay, I'm not going to go further, but the heterogeneity is not only in space, but is also in time, since when you study this kind of objects, you see that parts of this object also relax in an intermittent way. And that's something we did some time ago. And this is what you see. There are times when a lot of particles move, and there are times when you have that most of the system is immobile, in a sense that the system is relaxing by rapid bursts of mobility, which are sporadic in time. This is for a model Lennartson, this is a binary Lennartson system with Walter Kopp.
Correlated with the caging, like, because
No, this is basically between T star and the alpha structural relaxation. The caging is, you don't see movement at caging. There are harmonic motions. This happens. These are the events that that trigger the alpha relaxation. You have a few of these events relax. But the point is that not only the system is composed of different regions with different mobilities. The mobile regions are also intermittent. You have to spend long times without mobility to suffer one of these events. And this can be seen in very different systems. Here is super cool water with Francesco Sortino. These are the same kind of events. At some point you have a lot of mobility, and other points you have nothing. This is the same for silica. This is a corroboration, experimental corroboration in a polymer, glassy polymer, and we did this with Eric Weeks in Atlanta with confocal experiments in a colloidal system. But well, this was just to try to explain where that time scales came from in order to justify that we are choosing the kinds of the classes of molecules on the basis on what they are doing in the supercritical regime. That is, you have regions that are frozen and regions of defects, but they are not only defects, but they are also including their neighborhoods. Okay. It's not working again. I don't know how to change. No, it's not working. I see it in the screen, but I cannot see it there. Okay. Okay, here we are. Yeah, it works. Well, this is the second part. Today I'm going to speak on. Remember, we were talking on pure water. Now we plan to move to solutions. Next, we are going to speak about the hydrophobic interaction to finally reach what we intended to work in. That was hydrophilicity and hydrophobic interactions. So this is more from physical chemistry. When you have an ideal gas and a real gas, the difference is that the ideal gas, you have that the chemical potential depends on pressure. But when you have a real gas, you have interactions. When you have interactions, we have to define fugacity, that is some kind of effective pressure. And this effective pressure behaves differently from this behavior, in the sense that there are regimes when you have attractions that dominate and regimes where repulsion dominates. In this regime, for example, fugacity, that would be the tendency to escape of the molecules, is below pressure, so the chemical potential goes down. This is because we are in a regime where the pressure is low. If the pressure is low, this is the separation, this is the potential between the particles, the potential energy, and if we are here, you are feeling attractions. You are feeling attraction, you have less tendency to escape. But if you are in this regime, you are at high pressure, you enter the repulsive part of the potential, and the molecules, the particles, have higher tendency to escape than if there were no interactions. Of course, ideal gas is mixed because of entropy. There's no enthalpy. But when you have a non-ideal mixture of gases, you have to consider entropy since there are interactions. So if we move to liquid mixtures, we move to solutions, we are also going to speak on the chemical potential. And for an ideal solution, the equation is very similar to that of a real gas, but you have that the chemical potential is some reference state here, plus RT, the logarithm of the concentration, the molar fraction. Instead of pressure here, we have the molar fraction. But this is the case of the ideal solution. But if in your solution you have interactions, you are going to use here, instead of the molar fraction, you have to put activity that is in the same sense as fugacity, some kind of effective concentration. And you can write down the chemical potential in terms of the reference state and this activity coefficient, the activity of the system, that is the molar fraction plus the activity coefficient. The point is that in electrolyte solutions, you cannot decouple the effect of the ion and the cation. You have to use mean values, both for the chemical, for the activity and for the activity coefficient. When you try to measure this system, it would be interesting to measure the activity coefficients alone, since, for example, in biology, this is very important, since in very systems where you require specificity. But this is problematic. One possibility would be to use selective electrodes that are sensitive to the activity of one of the species. The problem is that when you measure this, usually you have a problem here. There's a juncture potential that is very difficult to measure, since when you have very small changes here in the juncture potential, it translates in very large errors in the measurement of activity. So the potential of the electrode changes a lot, and the errors in activity are very increase progressively as activity grows. So since there are these great difficulties in measuring experimentally activity, we can try to see if we have an acceptable theory that can give some value of the activity coefficient. The first theory that we consider is the Weis-Hückel theory. Most of you must be familiar with people who are from chemistry. I don't know if in physics you are familiar to the Weis-Hückel, maybe. But in the Weis-Hückel, you consider that when you have a strong electrolyte that is dissolved in water, it dissolves completely, and each ion is surrounded by water molecules and by the rest of the ions. And the Weis-Hückel theory accounts for these interactions, treating the solvent as a continuum. When you consider an interaction, it's a Coulombic iteration that is modulated by this epsilon here, that is the permittivity of the solvent. The postulates of the theory is that the strong electrolytes are completely dissociated in two ions, that the deviations that we are going to observe are due to the electrical interactions between the ions, and the third point that the ions attracts charges of opposite sign and repels charge of the same sign. So in some sense, you are going to have that the electric field is in part shielded by the other ions, and the basic postulate of the theory is that each ion is surrounded by what is called the ionic atmosphere, that this is a mean field theory, and each ion is surrounded by a sphere of oppositely charged ions. And this sphere is going to have some size, and the theory is going to try to calculate this size. In a medium with a certain dielectric constant, we can write the potential of the ion. That would be proportional to the charge of the ion, and again, it's going to be modulated by the dielectric constant of the solvent. And the presence of the rest of the atoms is going to alter this potential. And the Weis-Hückels tries this, calculating the electrical work of introducing one ion into a solution. You use the Born cycle. The ion is not charged, it's introduced in solution, is charged, and you solve the Poisson equation in the approximation of the concentration of the rest of the counter ions is proportional to interaction energy with the central ion, and what you get is this function which is dominated by this exponential here, where you have a kappa value, that kappa is an inverse by length, which has the inverse units of length. In this sense, this potential depends only on this parameter here, the inverse by length, whose 1 over kappa gives you the size of the ionic atmosphere. Here you have a simple plot where if you don't have screening, you will be here, but when you increase concentration of the solution, you move here, so the potential falls down more quickly. So kappa would be proportional to the dielectric permittivity, of course, to the absolute temperature, and also to the ionic force. The ionic force would account for the rest of all the charges that are in the system, all the electric field that could be contributed by the same electrolyte, and also if you have another kind of electrolytes in the solution. So if you have a high concentration of ions, this is going to be high, kappa is going to be low, and so this is going to fall as it happens here. So the size of the ionic atmosphere depends on the ionic strength, on the number of charges you have in your system. And in this sense, what is important is that you can calculate the activity coefficients, but of course you are going to be able to obtain mean values for the activity coefficient. The limited application is that you can only use very diluted solutions, and the problem is that for this theory, all ions of the same kind behave in the same manner, since there's nothing here concerning size of the ions. So ions of the same charge are going to give you the same result. Well, this was changed by the mean spherical approximation that explicitly considers the size of the ions, and it is in the same spirit. What was in the Weis-Hückel model was accounted for with kappa. Here is 2 gamma here that gives again a size of the ionic atmosphere. And again, you can calculate with this theory the mean activity coefficient. This would be the Weis-Hückel, this would be the mean spherical approximation. And when you consider the size of the ions, you must not only consider the crystallographic radius, which we are going to see later on, but you should consider that the ions are hydrated and they move with their water molecules around them. So there would be some kind of effective radius, and this diameter of the ions would be proportional also to the concentration of the solution. And the predictions are much better, are much closer to experiments. Okay, so In the case of ionic hydration, you have that when you form the solution, there should be interactions. The solute will interact with other solutes and also with water. When you dissolve an ion, like here, you will have the different spheres of hydration. And the ion is going to exert an orientational force on these water molecules, which are going to orient in a very strong fashion towards the central ion. And this orientational force is going to compete with water-water interactions, since this is going to try to disrupt the structure of water, the hydrogen bonds of the solvent, and also with the destructive effect of thermal noise. In certain consideration, we can think of this as if we had a primary hydration here, which is the first shell around the ion. Very close to the ion, you have a high electrical field, so these water molecules are strongly oriented and very ordered, much more ordered than in the bulk. Then we're going to have a secondary hydration, which occurs at larger distances where the electric field goes down, but this water is going to be less oriented, but they are going to still feel the effect of the ion. And in this sense, they can be more perturbed, and they can be more disordered than pure water. And then you are going to have a shell of normal water that at larger distances, water basically does not feel much this ion since it is screened. In this sense, when we look for ion-ion interactions in water, we have to take into account all these effects of all these kinds of interactions, the primary hydration and the secondary hydration. In this sense, the interaction between ions of opposite charges would be mediated by the surrounding solvent, by the surrounding water. And you can have three different situations depending on the strength of the different interactions involved. In some case, you can have here that the ions have a very strong hydration spheres, so they are going to be screened. In this case, the screening is less, so you are going to have the two ions at a closer distance, and at some point they are going to collapse. And this depends on whether on the kind of interaction, how strong is the interaction between the ion and water, and how easy or not is to remove water from the hydration sphere in order to bring the ions into contact. The interesting point is that in these two cases, the entropy change is going to be positive, since some water molecules are going to be liberated from this region to the bulk, where they can move more freely. So entropy is going to contribute positively to these cases. Okay, one thing we can measure or even calculate in molecular dynamic simulations are hydration numbers, and these are going to depend a lot on the method you use, but we can derive some tendencies. Basically, we are trying to see how many water molecules are surrounding each of the ions, and this, of course, is a dynamical equilibrium, so water molecules are going to interchange it between the primary hydration layer and the bulk. We are trying to count how many molecules the ions have in their primary hydration layer, and it can be and this can be, for example, estimated from measurements of hydrodynamics that can give you an idea of the size of the hydrated entity, and you can, in some sense, derive the number of water molecules that are surrounding each kind of ion. Here, for example, is a table where you see this is lithium, sodium, and potassium. You have the same charge, but the charge density goes down in this series, and so the hydration number for lithium is the higher, since you have a very small ion which has the same charge as in, for example, sodium or potassium, but the charge density is higher. And when you move to ions with higher charge, of course, you are going to see more hydration. Hydration numbers are going to grow. This was expected. You can also measure or calculate hydration dynamics. In this sense, you can calculate these R numbers, which are the time, the residence time of the water molecules around an ion, divided by the residence time of a water molecule in the bulk around other water molecules. And if this gives you a large number, we are going to speak of positive hydration, since the water molecules spend more time around the ion than around other water molecules. And if you have a value lower than 1, we're going to speak of negative hydration. The ion is not going to be hydrated, or it has to be hydrated for very short times. And these residence times can be measured by different techniques, like dielectric relaxation, NMR, or viscosity, for example. Considering viscosity, of course, there's going to be a relationship between hydration and viscosity, since the viscosity of the solution is going to provide us information on the hydration dynamics, since friction between the different water molecules is going to change depending on whether the water molecules are hydrating the ions or not. And this can be right down here, but this equation, this Schoen-Dole equation, where this is concentration, and the coefficient B is called the Schoen-Dole coefficient, which is related to the solute-solvent interaction. Here we have this coefficient for different ions. For example, this is lithium. This is larger than, in this case, larger than 1, but we also can have very low values for this coefficient, close to 0, and also negative values. If the ions are very hydrated, you have B values higher than 0, but if they are not hydrated in an important manner, you are going to have very low values of negative values of B. If you, for example, compare lithium to sodium or potassium, you see that lithium has the highest value. So lithium is going to be very tightly hydrated. And this can be correlated also to the to entropy of hydration, and ions of the same class usually show some linear behavior. So in the case of B positive, we speak of positive hydration. The water molecules will be very tightly bound to the ion. They will be very restricted in their motion. So we will have entities in which the ion has a very rigid sphere, and these spheres, this rigid hydration is going to increase the friction in your system, is going to increase the viscosity. But when B is negative, we speak of negative hydration. Water is around the ions is less restricted in its movement, so we are going to have less friction. And this would be, of course, related to entropy, restricted water or free water. This entropic contribution is due to the solvent, and this is important since when we are going to speak on hydrophobic interaction, we're going to see that it's an entropy-based phenomena. Okay, this is another definition, that the hydration can be related to what is called a structural temperature. That would be, it is defined as the temperature at which pure water has the same value for a given property, for example, viscosity, as the solution has at 25 degrees. And then when the structural temperature is lower than 25 degrees, we speak of positive hydration, since you have that the presence of the ions has increased the viscosity to values that could be attained by pure water at lower temperature. And when we have the case of the structural temperature higher than 25 degrees, we are going to speak of negative hydration, and the ions are going to have a reduced viscosity, which can be obtained at a much higher temperature. Okay, so when we speak of hydration, structure of ions, we have to take into account the different interactions between ion, and ion water. But when we speak of ions, we are going to take into account that the ions are not moving alone. They are moving with a hydration sphere, and this sphere could be very tight or very loosely bound to the ion, or it can be very rigid, or it can be exchanged very quickly with the bulk. In this sense, the crystallographic radii are not going to be compatible with the transport properties of the solution. And we are going to speak, of course, of hydrodynamic radii, which can, in the case when we consider the hydration sphere. This is, for example, the crystallographic radius for lithium, sodium, and divalent cations here, and these are the hydrodynamic counterparts. You see, for example, that for lithium, you have a very low crystallographic radius, but this radius grows a lot when they are in solution, and this is not strange. This is around the distance of a water molecule, since you're going to have your ions surrounded by a sphere of water molecules. And in this sense, this does not change much in this series, but again, when you move from lithium to sodium or to potassium, this radius shrinks a bit, because these water molecules are going to be less tightly bound to the ion, and they are going to interchange it more quickly with the bulk. Of course, when you have divalent cations, you have more charge, and you're going to have a bit higher hydrodynamic radius. So it's not just a matter of size. There are a lot of considerations you have to take into account. And some people speak of ions which promote or destroy structure of water, but in general, this is not rigorous. And this hydrodynamic radius, of course, can be calculated by viscosity measurements. For example, here you have the Stokes radius, that when you relate the radius of the ion with viscosity, and you can go to the diffusion coefficient, which again relates the radius of the ion to viscosity, and you can measure these quantities. Well, hydration structure can also be investigated by means of molecular dynamic simulations, and these were very early simulations where the people looked at different kinds of ions and looked at the hydration water around them, and they could calculate, in some sense, some radius of hydration. Okay. One interesting observation was the heliotropic series. That this was a very old observation in which certain salts increased the solubility of globular proteins, And this was a series that was not very well understood, but you have a series for anions and also for cations and for Hull sales here. And it is not easy to explain, but it has to do with the specific interactions of these ions with water, and how this interferes the interaction of water with the protein. And what is important is that very interesting practical applications. We're going to come back to this a bit later on. Okay, here. And we can speak of cosmotropes in the sense that there are ions that promote the order of water, that interact strongly with water, and in that sense, they are preventing water molecules to interact with proteins. And so this preserves the integrity of the globular protein, since the water molecules can attack the surface of the protein and can fight for the hydrogen bonds that sustain the secondary structure of the protein. So in this sense, if you are you are taking these water molecules from the protein surface, you are preserving it. And this is the role of a cosmotrope. If you don't have ions, water is going to interact with the solute, with the protein. And in the case of the chaotrope, they are entities that promote chaos, disorder. And in this sense, they are not hydrated or repel water, and water molecules are more, they favor the interaction of the water molecules with the protein, where they can compete with the internal structure with the backbone hydrogen bonds, and they can also lead to protein denaturation. Not only the backbone hydrogen bonds can feel this effect, but there is also the effect of the interaction with the side chains of the protein, so that there could be a lot of different behaviors, and the picture is not always so easy as here. Okay. In the case of hydrophilic substances, which are not ionic, we are not speaking of charges, but we are speaking of molecules which are polar. And in that sense, these molecules can form hydrogen bonds with water molecules. And it is interesting that these systems can form interactions, but this would depend not only on the presence of these hydration sites where they form hydrogen bonds, but also in the orientation and the availability of these hydrogen bonds. For example, here we have sorbitol and mannitol. They are when you look at the solubility of sorbitol, is 2.5 times greater than that of mannitol. And how can you explain this? Well, you can explain this considering that these hydroxyls here in sorbitol are more exposed to water, and so they are better to form hydrogen bonds, while in this one, these eclipsal positions are less easy to interact with water. So this molecule is going to establish better interactions with the solvent, and in this case, you are going to interact less. This is also the case of the different anomers of glucose, where you have the alpha and beta anomers. And again, here you have a difference in the position of these hydroxyls. Here you have one more hydroxyl in the equatorial position, which is more able to interact with water, and so it's going to be more soluble. Well, what about hydrophobic substances? When we are going to have to consider different situations. The first case is when your hydrophobe is very small. When the hydrophobe is very small, we can have the possibility that the water molecules arrange around them in what is called a cult rate, in the sense that the water molecules are not sacrificing any hydrogen bond, and they are forming a cage for this molecule. This is, for example, one of the ways in which methane is expected to be at the bottom of the oceans. And, you know, water does not form good interactions with the molecule. What it's going to try to do is to sacrifice the less interaction as possible. And this can be done here without any sacrifice. So the clatrates are a good option when you have to put in contact a hydrophobe with water. But this is only possible for very small systems. When the system grows, you're going to have a problem that there would be a disruption in the hydrogen bond arrangement or network of water. These nonpolar solutes, you are going to see they attract each other in the sense that, for example, here we have two small solutes, two methane molecules, and when they are far apart, both molecules are fully hydrated by water. These water molecules which are in contact with the hydrophobe are in an unfavorable position since they are sacrificing one hydrogen bond. They cannot form hydrogen bond with the solute. But then when you look, for example, this potential of mean 4 calculation, you see that at some point these two small solids are going to collapse, and they are going to release water to the environment, to the bulk. But this has a cost, since, as we will see later on, there is a cost of dehydration. It is not that water dislikes the hydrophobic substance. It's not like polar likes polar and a polar likes a polar. We're going to see that non-polar substances are also hydrated. There is hydration. But the best situation is when these water molecules are liberated to the bulk. And this barrier here would be the cost to remove these two until they are placed in the bulk. When the surface is extensive, you are going to have problems, since water molecules have to place in contact with the surface, and in that case, there's no way not to sacrifice hydrogen bonding. And this is, there are several theories that predicted that there would be some kind of depletion of density at the surface, and it is what is seen here. This is a plastic system, and water molecules don't like to be close to this system. You're going to see here a region of density depletion. And when you have two of these plates, you are going to see this at the two sides, and at some point they are going to collapse. This is, I don't know what time is it? Okay? Okay. So at some point we are going to have the collapse of the two plates, and This is what we are going to study next, that is the hydrophobic interaction. And it's the basis of several relevant several relevant situations, like, for example, protein folding. The point is that this is a perfectly flat, structureless surface. When that's not the case, like here is what, this is another hydrophobic system. These are self-assembled monolayers, which experimentally you have a substrate, like, for example, this gold surface. You have some thiol binding to alkylic chain, and these alkylic chains can be functionalized in order to be hydrophobic or hydrophilic. These systems were very popular from experimental and also from a theoretical point of view. And in this case, you have structure at the surface. Here you have the central gold atom, you have the alkylic chains, and you have, for example, a methyl ending, so this is going to be hydrophobic. But this, here you have a structure and you have interactions. These interactions are going to be low, but you are going to feel, the molecules are going to feel van der Waals interactions, and you see no depletion density here. When you look at the density profile, you see that you have layering. Water molecules are hydrating this system. So you see here a peak that is very similar to that in hydrophilic systems. So you are going to have hydration. The point is that, again, if you have two plates made of this system, you have one here, they are indeed going to collapse by the hydrophobic effect. But it is not that water dislikes them and it's going to be easily released.
All the surface is hydrophobic, because you could have in principle a surface that, larger surface that you have one layer of molecules that are hydrophobic, another hydrophilic. But this
this here is all hydrophobic. What is in contact with water, you have here two phases, but look at one of them, is completely hydrophobic. You have two of these plates, the plates are going to collapse. So this is going to lead us to the next subject, which could be hydrophobic interaction. I don't know what time is it.
It's
time?
5 to... in principle, you have another half an hour.
Half an hour. Okay. Maybe I could stop here for rest. What do you think?
5 minutes rest. Get a coffee. And in 5 minutes back. Okay?
Okay, so we came to the concept of hydrophobic interaction, which is not an interaction itself. There's no interaction in hydrophobic interaction. We are going to see that it's an entropic effect that is due to water. But it's called in this way since it involves a collective process. This is a very important effect that drives the cell assembly of many systems, for example, globular proteins, or also micelles or membranes, or even systems in material science. So it's a very important effect that has very interesting practical consequences. Which is the thermodynamics of the hydrophobic interaction? You know, the solubility of nonpolar substances in water is low. But again, it is not that water dislikes them. Water likes water a lot. That's the problem. And it is not only that the solubility of nonpolar substance in water is low, but it is also strange in the sense that it decreases when you increase temperature. In general, when you have the dissolution of ions or an electrolyte in water, you increase temperature, you have more solubility. Well, in the case of the hydrophobic interaction, you lose solubility as you increase temperature. Thus, this should mean that thermodynamically, the free energy of solubilization, which means the free energy of transfer of the nonpolar system from its medium or from vapor phase to water, increases when we increase temperature. And this free energy of solubilization, of course, has an enthalpic and entropic counterpart, and it is positive. Okay, if we assume that these two, the entropy and the enthalpy, are not going to change much in a low temperature range, they remain basically constant, this increase in the free energy of solubilization should come from the entropic term, in the sense that in order, if this is not changing and this is not changing when you increase temperature, this should mean that the T plus delta S should be negative in order that its negative counterpart is going to be positive, and you are going to have here positive free energy of solubilization. So the message is that solubilization of a nonpolar solute in water involves a decrease in entropy. But when you dissolve something, you have mixing term. You are dissolving a system in water, and you are increasing information, or increasing entropy. Thus, there should be another source of this entropy loss that must be compensating and even being much larger than the entropy gain in the mixing process. Where does this come from? Well, one could think that the internal degrees of freedom of the molecule could be related, but when you study very simple systems like monatomic gases or systems which have no important internal degrees of freedom, you again have this contribution. So the contribution should come from water. There's no other way. These are data for different small alkanes, and you have the free energy of solubilization, you have the enthalpy and the entropy change, and you see entropy is always, the change in entropy is always negative. But you see here that enthalpy is not always playing against. Here you have attractions between the nonpolar substance and water. But this is more than compensated by this entropy loss. This entropy loss is what is governing the full process. This term, this entropy loss, is due to the effect of water. Okay, this is, for example, the transfer of a nonpolar solid from its medium to water, and you have here the chemical potential. You have the change in, also the changes in enthalpy and the entropic term. You see that at high temperatures you can, well, this is always positive. This is always positive. Again, the systems are have very little solubility in water, but this changes with temperature. And you see that here you have that this is the entropic term that, of course, increases with increasing temperature, and this is the enthalpic term. For many systems, it happens what we saw in the other table. When you are at around room temperature, you have attractions. It is not that the system is repelling water. It attracts water, very little. You have small interactions. You have van der Waals interactions, for example, but there are attractions. And the whole process is driven by the entropy effect, and this entropy effect comes from the solvent. Well, there are several experiments that can be done, for example, relaxation experiments that test the effect of hydration on the local interactions in the system, the interaction of the solvent with the nonpolar molecule. Here we are showing the electric relaxation times for water per mole of solute. Here is water and I think it is a series of alcohols and carboxylic acids of different chain length. And you see that as the chain length increases, you have a shift to larger relaxation times. And this implies a greater decrease in this entropy of solubility. So the restriction in the movement of the water molecules produced by the presence of the hydrophobic surface is what drives the process. You have a longer change. You are imposing more restrictions on the vicinal water molecules, and this is causing the entropy decrease. Here we have NMR studies where we have water with acetone, and here you have the case of this is the concentration of acetone in water, and basically what we see is the presence of this molecule slows down the rotation of water, but this happens when you have low concentrations of acetone. This decreases the rotational motion of water since these time scales begin to increase, but at some point this tendency changes since at some point you're going to have a solution of acetone. Instead of acetone in water, water in acetone is going to change. But this restriction is what matters, since water around acetone is more ordered, is less free to move. Unlike the case of water, acetone does not show much. The relaxation times are not sensitive to the presence of water. So also the mobility of water depends more on temperature, since here you see a very important change, and for acetone it's always basically the same. Okay. So we are going to study dynamics and structure and the thermodynamics of the hydration process, of the hydrophobic interaction.
Just one question. So the argument is that in the dominated by the negative entropy in the sense that when it dissolves, not thinking about the surface, but when it dissolves the solute, water gets less mobile.
Yeah.
But this is not true to any, if it's hydrophobic or if water will become less mobile, less moving, or in the case of the hydrophilic, because it's binding, it might move more.
Yeah, but in that case, you're going to have an entropic contribution that you lack in the other case. So the free energy would be dominated by the enthalpic term.
Okay.
So in the case of the hydrophobic system, your enthalpic term is very little.
Yeah.
But it's not negative. It's not positive. It can be negative, but very little, very small.
So it's dominated by entropy.
It's dominated by entropy. In the other case, you have attractions. Yeah, yeah. The mobility is always, of course, going to be even the mobility reduction could be even worse, but you're going to have a compensation of enthalpy.
So the very definition of something hydrophobic, hydrophilic, is if it is energy dominated or is it is entropy dominated?
I would not say that it's such simple. There can be other subtleties. We're going to see, but in some sense, it's correct. It's correct. So, okay. When we have nonpolar substances dissolved in water, these hydrophobic groups are going to interact between them and to the water molecules with very weak interactions, for example, van der Waals forces. However, hydration, as we saw, could be also negative, and that's why we speak of hydrophobic hydration. It is not that the hydrophobe is not hydrated. It is hydrated, and there are interactions, but such interactions are low. Estimates of the relaxation time of hydration water, based, for example, on total relaxation times, could be very large values, which shows that this effect can extend at more than one hydration sphere. And solvents, for example, acetone, rotate faster than water, so there should be no bond between water and acetone. The point is that water is more related to other water molecules. It's trying to exclude the hydrophobe, and the restriction comes from for improving water-water interactions and not for interactions between water and the hydrophobe. Since, for example, this molecule surrounded by water rotates basically freely. Computational simulations are very important in this field, that can give us very interesting information. If you have small solutes, water could have very low residence times, but in that case, as we saw before, they can, for example, arrange themselves in very strong hydrogen bonds in order to avoid the small hydrophobe. So these water molecules are going to be very strongly related to each other, and it's going to move very, very slowly. If we consider flat walls of hydrophobic systems, you are going to have thermal vibration. And you can see that water modifies the properties at relatively high distances from the wall. There are studies experimental studies that show that 10 nanometers, but in other cases it could be more than that. There's no consensus on how many water layers are affected by the hydration process. And of course, the hydrogen bond network of water can show improvement in order to structure to avoid the hydrophobe. It's possible that you have hydrogen bonds that are more relevant here or more stronger than in free water. This means that the hydrophobic wall can induce an improved structure in the water in contact with it. Thus, we saw that the hydrophobic interaction produces a decrease in the entropy and solubility of hydrophobic substances. Since these nonpolar systems induce restriction in the movement of the water molecules, which in turn produces a decrease in entropy. This could be the nature of the hydrophobic interaction. It could be the finite interaction that occurs not only van der Waals forces between the nonpolar substance and water. It's also the effect that that tends to reduce the solvent exposed area. That is, if you had, for example, two molecules, two nonpolar molecules, or two walls, two solutes, this you will have this situation. This is for one of them, it will be hydrated. Water molecules are not comfortable here since they don't have large interactions with the wall. So, but they are going to be more restricted in their movement. You have here another surface. The perfect situation is to come together and release water molecules to bulk. These water molecules are going to increase entropy since they can move more freely when they are in the bulk. This is the nature behind what is called the interaction, the hydrophobic force. It's not a force, but it's like a force. It attracts the two walls, but it attracts the two walls because water wants to be away. It is better here than here. If you have a single flat wall, water is going to be here. In some kind of sense, it would abhor vacuum. It's going to hydrate the surface. But the best situation is that you have two surfaces is to collapse and release water. This is the basis of the hydrophobic collapse, for example, in proteins. Okay. This is the same slide I showed before. For example, we have two small molecules, hydrophobic molecules here. These two molecules would like to be together and release two water molecules, but this has a cost. You have hydration here. This hydration could be negative. So you are going to have to surmount a barrier and then going to, in this potential mean force, you're going to find here the optimal situation. But it has a certain cost. So the total interaction is going to include entropic and enthalpic contributions, which would be related to the different arrangements of the water molecules. And you're going to have these two terms, but the point is that you are looking at whole contributions. In this sense, when you look the system only from the thermodynamic standpoint, you are mixing things. You are not going to see the specific interactions. You're going to see a global effect. That's important, interesting, but you are losing specificity. You are not grasping all the details of the process. So at some point, it is interesting to go at a molecular level and not just to keep the thermodynamic macroscopic effect. Okay, well, what about, well, this is the length of the hydrophobic interaction. I said it before. There is no consensus. There are people who say that it's very local, and people who say that measurements can tell you that you're going to feel the effect at very, very low distances or very large distances. There's no consensus, but it seems that it's no more than a couple of hydration layers. And what about temperature? assuming that the temperature change is small, these two things, neither the enthalpy nor the entropy is going to change, they are constant, and that this is going to be positive. It could mean that if you increase temperature, you're going to lead to a decrease in the free energy, what we saw before. But we should also take account that we are speaking of the behavior of water, and water is a structural system. And if you increase temperature, the structure of water is going to feel the temperature change. So if you change temperature too much, perhaps you are not gaining so much by releasing water molecules, since they are not going to be very well structured at the bulk. So this effect is not going to have a trivial temperature behavior. Many different things, many different effects are at play. They mutually interact, and it could be quite complicated. In fact, at certain temperatures, you could see a positive entropic contribution, and you would see a decrease in the order of water, and then this contribution could be weakening instead of strengthening the interaction, the hydrophobic interaction. So it is expected that above certain temperature threshold, the effect is going to revert. Well, what about pressure? There is also cold denaturation. For example, in proteins, this is related also to the hydration of a protein, and you can have problems with increasing temperature or decreasing temperature. So you have to be very, you have to be very careful when studying the hydrophobic effect. What about pressure? At high pressures, we know that water begins to lose its tetrahedral organization. So it is expected that at high temperatures, this effect is going to disappear. Water is going to turn into a normal liquid, since there's no gain in releasing water molecules to the bulk, since in the bulk they are not ordered. So again, pressure plays against the hydrophobic interaction. This is also important for proteins, which could be denaturated at high pressures. Well, which other factors modify the hydrophobic interaction? Well, one of them is the addition of substances which destroy the order of water, as we saw before. These substances can form hydrogen bonds with water, but can form hydrogen bonds that perhaps are not compatible with the rest of water's inherent network. So these molecules could be altering the ability to form, of the water molecules to form hydrogen bonds with other water molecules. And thus, these substances, which destroy the structure of water, again, are going to play against the hydrophobic effect, since you are not gaining much in going bulk. This is the case, for example, of urea that denaturates proteins. There is also the addition of substances that play in the other sense. They promote the structuring of water, for example, certain sugars, which have a hydration structure that is very compatible with water. They stabilize the structure of water. In fact, for example, they are very used in the cryogenic industry. And these substances are going to increase the hydrophobic effect. They promote the hydrophobic effect. Okay, but the point that Marcia asked is what is to be hydrophobic? Do we have a definition of do you have a scale for hydrophobicity? Do you have absolute values or relative values? I don't know how much time I have. You know, it's a good time then to. So you have to wait for tomorrow.
What makes hydrophobic or hydrophilic? Next chapter of the soap opera, Water, Friends and Enemies.
Okay, thank you.